Hello everyone. Today, our group will be presenting our project titled Simulation of Rankine Steam Cycle. This project was completed by our group members, Amanda, Charlotte, Danish, and Amirul. This report presents the design and simulation of a Rankine cycle using Aspen Plus aimed at producing 10 megawatts of net power. The study includes mass and energy balance calculations and an analysis of the thermodynamic performance of each component. It also explores systems modifications to increase the net power output to 20 megawatts with the updated configuration evaluated for efficiency and feasibility. Key findings cover cycle efficiency, enthalpy distribution, and performance improvements from the system upgrade. The study supports the development of optimized power generation systems for industrial use. These are the contents of our project we'll be presenting today. This report presents the design, simulation, and performance analysis of a Rankine steam cycle system using Aspen Plus, developed in response to the growing global demand for energy and the urgent need to reduce greenhouse gas emissions. The system is designed to generate 10 megawatts of net power for a manufacturing zone in the Samajaya Free Industrial Zone, Kuching. The Rankine cycle, widely used for converting thermal energy into electricity, is especially effective in recovering waste heat from sources such as biomass combustion, geothermal wells, and industrial processes. The cycle consists of a pump, boiler, turbine, and condenser with advanced configurations incorporating reheating and regeneration to enhance efficiency. This project also involves modifying the 10 megawatt system to achieve 20 megawatt net power output by increasing the working fluid flow rate, raising boiler pressure, and improving the overall design. Aspen Plus is used to model key components, calculate thermodynamic properties, perform mass and energy balances, and carry out sensitivity analysis to assess efficiency, feasibility, and operational safety. The study aims to meet client requirements while demonstrating how thermodynamic principles and simulation tools can be applied to design and optimize modern power systems. This report presents the design and simulation of a Rankine cycle using Aspen Plus aimed at producing 10 megawatts of net power. The study includes mass and energy balance calculations and an analysis of the thermodynamic performance of each component. It also explores systems modifications to increase the net power output to 20 megawatts with the updated configuration evaluated for efficiency and feasibility. Key findings cover cycle efficiency, enthalpy distribution, and performance improvements from the system upgrade. The study supports the development of optimized power generation systems for industrial use.
So I will be presenting the methodology part for our Rankine cycle simulation project, which will divide into two parts, the 10 megawatt base case and the 20 megawatt modification. So for the part A, 10 megawatt Rankine cycle design and simulation, we begin by creating a new case in Aspen Plus B14, which is a process simulation software used for thermodynamic system. The steam tables package was selected to ensure accurate steam and water property data. Water was added as the only working fluid, then 4 main unit operations were inserted. So for the first one, a compressor to represent the feed pump, a heater to stimulate the boiler, an expander acting as a turbine, and a cooler to model the condenser. These were connected in sequence to form a closed loop representing the Rankine cycle with process steam streams drawn clockwise. The feed pump was set to raise saturated liquid from 0.1 megapascal to 10 megapascal with an isentropy efficiency of 85%. The boiler maintained the 10 megapascal pressure and heated the fluid to 500 degrees Celsius to produce superheated steam. The turbines accepted steam at 10 megapascal and 500 degrees Celsius and expanded it down to 0.1 megapascal, also with 85% of efficiency. The condenser brought the enhanced steam back to the saturated liquid at 0.1 megapascal. A suitable mass flow rate was manually adjusted until the net output for the turbine work minus pump work equal to the 10 megawatts. The thermodynamic properties such as pressure, temperature, enthalpy, and entropy were recorded at all 4 state points. We used these values to calculate the turbine at pump work, net cycle output, boiler heat output, and thermal efficiency. Finally, we validated all Aspen simulation results using manual calculation based on the steam tables. Next, for the part B, 20 megawatt Rankine cycle modification. So for the 20 megawatt version, we duplicated the 10 megawatt simulation as a starting point. All state point properties were recorded again, and the same energy balance calculation were repeated. We then calculated the new thermal efficiency and compared with the 10 megawatt system. The performance comparison covered power output, mass flow rate, thermal efficiency, and enthalpy change across components. We again validated the results with the steam table to ensure accuracy. Finally, we acknowledged the limitations such as assuming steady state conditions, idle components, and the absence of cost or environmental factors. So this structured methodology helped us to simulate and compare two Rankine cycles effectively using Aspen Plus B14 and fundamental thermodynamic principle.
Okay, next, I'm going to explain about our result in Rankine cycle system. For the 10 megawatt Rankine cycle simulation, the mass flow rate of steam was set at 43,090 kg per hour. The boiler operates at 10 megapascal and produces superheated steam at degrees Celsius. At this point, the vapor fraction was 1, indicating that the steam entering the turbine was completely dry and in a superheated state. As the steam exceeds the turbine, the pressure dropped to 0.1 megapascal and the temperature decreased to approximately 99.6 degrees Celsius. The vapor fraction at this point was 0.9399, which showed that some condensation occurred during expansion, resulting in slightly wet steam. And for the 20 megawatt system, the same pressure condition was maintained, but the boiler outlet temperature was increased to 550 degrees Celsius to boost thermal energy input. The steam flow rate was nearly double to 80,650 kg per hour in order to meet the higher power requirement. At the turbine outlet, the vapor fraction improved to 0.9707, meaning the steam remained drier compared to the 10 megawatt system. This improvement in steam quality is beneficial as it reduces the risk of turbine blade erosion and support better overall efficiency. Next, here is the simulation that we created by using the Aspen Plus software. The values were chosen to get the 10 megawatt and 20 megawatt power output.
In this study, we use Aspen Plus to simulate two Rankine cycle systems in order to compare how different power level affect the system performance. The primary goal was to evaluate the impact of the scaling on energy efficiency, steam quality, and thermal behavior. The first configuration was designed to generate 10 megawatts of net power. For comparison, the second system was scaled up to produce 20 megawatts of net power. Both systems was modeled under the same pressure condition, which is 10 megapascal for the boiler and 0.1 megapascal for the condenser. This allows us to isolate the effects of power scale and temperature on the system behavior. The main difference between two systems was the boiler outlet temperature and the flow rates. The 20 megapascal system had the higher outlet temperature of 550 degrees Celsius compared to 500 degrees in 10 megawatt system. It also required nearly twice the steam flow to meet the higher power demand. These changes were essential for testing how temperature and mass flow influence the key parameters like efficiency and steam dryness. Now moving into the performance result. One of the most noticeable outcomes was the effect of the increased turbine inlet temperature. It caused a greater enthalpy drop across the turbine, which directly translated into a higher specific work output. This means that every kilogram of steam, the turbine was able to extract more energy. Another key observation was the improvement in steam quality. The vapor fractions at the turbine exit increased from 0.9399 in the 10 megawatts case to 0.9707 in the 20 megawatt case. In practical terms, this means that the steam leaving the turbine was drier, reducing the risk of the erosions or mechanical damage to the turbine blades. These observations align well with the finding of H and Mazok, both from 2024, who emphasized the importance of superheats and dryness in the turbine longevity. Despite the improvement in outlet and dryness, the overall thermal efficiency of the two systems remained very close, around 39% for the 10 megawatts and 38.8% for the 20 megawatt system. This confirmed that in the supercritical Rankine cycle, increasing the temperature or scale doesn't always yield the proportional efficiency gains. We start to hit a point of diminishing. Now let's discuss on the engineering challenges that come with scaling up a Rankine cycle system and the strategies we recommend to address them. When moving from the 10 megawatts to 20 megawatts design, the physical demand on the system component increased significantly. Not only do you have more steam passing through the system, but the thermal stresses, pressure loads, and material requirements all become more intense. Every component from the boiler to a turbine and condenser must be engineered to handle higher volumetric flows and maintain structural integrity under elevated thermal loads. One of the biggest material challenges is the need to operate the higher temperature 550 degree in our 20 megawatts case. This isn't something conventional steel can handle over long periods. We need the advanced heat-resistant material like nickel-based alloy. While this material increase system costs, they are essentially for a long-term durability and high-temperature reliability. This is in line with the finding of Marzok at 2024, who highlight the importance of material choices in high-temperature steam system. To further the improved performance, we recommend the integrating advanced cycle modifications, especially reheat and regenerations. Reheat involves the sending partially expanded steam from the high-pressure turbine back to the boiler, reheating it and sending it to the second turbine stages. This improves the overall steam quality, reduce moisture at the turbine exit, and increase power output. As Belos 2022 explained, reheat is especially effective in the larger system where maintaining the steam dryness is critical. Regenerations, on the other hand, improve the efficiency by preheating the feedwater using the extracted steam from the intermediate turbine stages. This reduces the energy required in the boilers and cut down the overall fuel consumptions. Regeneration has a strong impact on the fuel economy, especially in the mid to large scale system. Together, this improvement makes the Rankine cycle much more suitable to the industrial applications. In fact, this type of system design would be good fit in upcoming developments such as Samajaya Free Industrial Zone, where large-scale power generation is needed. This incorporating reheat and regeneration system can meet energy demands more efficiently while maintaining reliability and reducing.
Next, for the conclusion, to conclude this project, we successfully designed and simulate a Rankine steam cycle using Aspen plus V40. We work with two system configuration, one designed to produce 10 MW of power and a second one scale up to produce 10 MW. Both systems use water as the working fluid and was set up with the same boiler and condenser pressure. To achieve the higher output in the second system, we increased the boiler outlet temperature and almost double the steam mass flow rate. This change led to a greater enthalpy difference across the turbine, which increased the work output. We also observed that the steam at the turbine outlet was drier, which is beneficial because it reduced moisture-related damage to the turbine blades. Despite this improvement, the overall thermal efficiency of both systems remained nearly the same. This is common result in basic Rankine cycle. As further efficiency improvement usually require additional feature like regeneration or reheating. Through this simulation, we learn how each part of Rankine cycle affect the system performance. Using Aspen Plus help us visualize real-world condition and apply thermodynamic principle effectively. Overall, this project gave us valuable insight into energy system design and highlight the importance of steam quality flow rate and system optimization in achieving reliable and efficient power regeneration.
These are the list of references we have used for this project. And that is all from our group. Thank you.